You have fallen into Event Horizon with John Michael Godier. If you've been watching Event Horizon for a while, you'll know that John explores the mystery of the universe with his guests. Guests who are scientists, engineers, all thinkers, who took bold steps in their careers to get where they are. That's why we're excited to be partnering with our sponsor, Strawberry.me. Strawberry.me connects you with certified career coaches, real professionals who help you clarify your goals, build a strategy, and take meaningful action. Whether you're aiming for a promotion, making a career change, or stepping into leadership, this isn't guesswork. Career coaching with Strawberry.me is forward-looking, practical, and built for results. Think of it like mission planning, but for your professional life. None of us at Event Horizon had a linear career path. There was a lot of trial and error, figuring things out solo. But what if you didn't have to go it alone? If you're ready to stop feeling stuck and start making strategic moves in your career, head to strawberry.me/Event Horizon and take the short quiz to get matched with your certified career coach. It only takes a few minutes and could change everything. Strawberry.me/Event Horizon. Start your transformation now. You'll never regret investing in yourself. Thank you. In today's episode, John is joined by Aster Taylor and Tessa Frincke. Aster Taylor is a PhD candidate at the University of Michigan's Department of Astronomy and a 2023 Fanny and John Hertz Fellow. Aster is interested in the dynamics of solar system bodies, particularly their non-gravitational accelerations. They are also interested in the formation of giant planets and a myriad of other topics. Tessa Frincke is a PhD student studying astronomy and astrophysics at Michigan State University. She is a graduate from the University of Toledo with a Bachelor of Science in Physics with a concentration on astrophysics.
Tessa Frincke and Aster Taylor, welcome to the program.
Hi, thanks for having me.
Thank you very much for having us.
Now, you guys have found the third ever interstellar object, 3I Atlas, which recently actually got that name. It was up until just a few days ago being called by its original designation. What caused that? What was the renaming of the object? Is that just by following some IAU convention or something like that?
Generally, yeah. It is traditional that when we name an object like this, we name it after its discoverer. So 1I ʻOumuamua is a bit of an outlier because it was named by the IAU directly, but 2I Borisov was discovered by Borisov, and this object was discovered by the Atlas instrument, and so it's been named 3I Atlas pending IAU formal designation. I'm somewhat hopeful that we'll get that formal designation because all caps Atlas is not a great name, and it makes it very confusing with the actual instrument, but that's the general naming scheme behind these objects.
So they get designations, and this would also get a designation as a comet, right? It would have a completely separate designation.
Yeah, so I will admit that I am less well-versed in the comet designation. In general, I believe the format is C/year it was discovered, and then just a increasing counter of number of objects that have been discovered in this year. So in this case, it's C 2025 N1, but we will generally be calling it 3I Atlas for the foreseeable future, just because it is significantly more impactful as an ISO interstellar object than it is as a comet.
Now, this object is large compared to the other two confirmed objects. ʻOumuamua was tiny, and Borisov was relatively small, but this is up to 12 kilometers. Is that what are the constraints on the size of this thing?
So I will say that is an upper estimate. 12 kilometers in radius is an upper estimate for the size. The thing that we have to be careful with is that the way we estimate the size is we estimate how bright it is. We can calculate that from observations. And then we say, okay, how big does this need to be for a comet-like reflective object to be this bright, given its position and given where the sun is. And if you do that calculation, you find that it's 12 kilometers, which is that implication. Unfortunately, though, if there is a coma, the coma also contributes to the brightness, but not to the size. And so the presence of a coma means that this is a definitely an upper estimate and not a true value. We can also sort of say that this is almost certainly not the real value. I would estimate it's more like 2 kilometers across, which is still large, but not so large as 12. And the reason that we would make that estimation is we can calculate the number density of these objects in the galaxy, and we can calculate how big the object is and how much matter there is in it. And we can calculate how much matter per star needs to be ejected in ISOs in order to make this number density. And the answer is 1/10 of a solar mass per star, which is way too much. The average star is 0.5 solar masses, and that means you get 5 times as much mass in stars. But there's the additional problem that stars are made of gas, and these are made of what we astronomers call metals, which are much less abundant. And so the end result is that in order for it to be 12 kilometers across, you would need to have the galaxy be 200 times more efficient at turning matter into ISOs than it is at turning matter into stars. And we just don't believe that that's possible. And so we can make a much more reasonable calculation of, say, okay, instead of what if it was 100 Earth masses, and that implies an object about 2 kilometers across. And that's a far more reasonable answer. And so we're pretty confident that that 10-kilometer answer is wrong. We don't know what the actual value is, but it's certainly smaller than that, probably around 2 kilometers. That's still very big, but that's what we're working with.
Now, what is the average size of a regular solar system comet in comparison to that?
It depends, and Tessa, feel free to jump in at any time. It depends very heavily on what you define as the average. The vast majority of objects are going to be small, just because there's far more of them. The vast majority of objects we've detected are going to range from, I want to say, like 100 meters up to like 5 kilometers. We've found objects as large as 10, 20, 30 kilometers, but not very many of them. And we know there's tons more smaller than that. There's tons and tons and tons of little dust particles and pebbles scattered throughout the solar system, just because small things are much more common.
Yeah, I would agree. They have a range of sizes, but I think that 1 kilometer to up to maybe like 25 kilometer on the large side. But
now, Tessa, about the hyperbolic trajectory of this object, how does this differ from ʻOumuamua, for example? It's because this is moving faster and it's coming in at a different angle. How is it deflecting as it passes near the sun? Is it more marked, or is it just going to barely be deflected? Or will this go off in a completely different direction? And what direction in the galaxy did it come from?
yeah, so the comet was coming in from an angle, and it just passed within Jupiter's orbit, and it's at about 4 AU from the sun right now, and it will pass pretty close to Mars at some point in early October, and then it will get pretty close to the sun at about 1.3 AU, and then come back out at a similar angle, similar to the angle that it came in at a pretty high speed. Coming in fast, leaving fast type of trajectory.
Guys, recall it's like 60 kilometers per, that's fast.
Yeah.
Which,
Super fast.
What does that tell you about the potential age of this object, Aster, that it was moving so fast? Because you remember, ʻOumuamua was out at the local standard rest. It wasn't really moving.
Yeah, exactly.
Compared to the solar system. This is cooking through. Does that tell you that it's a younger or older object?
That tells you that it's older. The way that the galaxy works is as stars form, they form in the thin disk of the galaxy. And then over the lifetime of the galaxy, they get kicked up into higher and higher orbits and go faster and faster. And so you can calculate for a given galactic galactic velocity, what the expected age of this object is. And for this object, from the velocity alone, you'd expect it to be about 10 billion years old. And if you do a more advanced calculation, and I have a paper on this that'll be out pretty soon, hopefully, it's more like 3 to 11 billion years old. That's significantly older than ʻOumuamua, which, as you may recall, was about 100 mega years old, maybe up to 1.5 billion years. And so the fact that it's moving so quickly means that it is much, much older than ʻOumuamua. I will also say, by the way, that the direction that these objects come from doesn't matter very much at all. The effect of the stars is to kick them around a lot. And so by the time they've gone a few parsecs away from the solar system, we'll have no idea what direction they're going in, just because the stars will have kicked them around into random, almost completely random directions. And so we can't learn very much from that alone, unless it's very young, like ʻOumuamua. And even still, it was just a little bit too old for us to get any reasonable estimation of which system was its parent.
Yeah, you can't really figure out what system, but you can. What could you tell about the type of system? In other words, can you characterize what this thing is made out of? And I find that really interesting because I would definitely would like to see an 11 billion year old rock, you know?
I think we all would.
Yes, I think there's obvious reasons for that because that's very early.
Very early.
You know, very early. And that could be some of the earliest material that you know, other than gas, that formed.
100%.
Yeah, and that tells you something about planet formation that early.
Exactly.
You know, that's good stuff. What can you tell? So what can you tell about the composition as observations continue? What can you determine about what this is made out of?
So right now we can't tell much. Our observations we haven't had enough spectra of high enough detail to get anything super comprehensive. We can tell it's probably had some volatiles in it because we can see the outgassing, the coma, which we presume is from outgassing. But we'll have to see as it gets closer to the sun if that gets more and more active. Other than that, I'll actually leave this over to Tessa, who is doing some observations at this object right now that will hopefully be able to give us some insight there.
Yeah, for sure. I mean, like, it's speculated that interstellar objects are ejected through a gravitational interaction between, like, the larger body, like a planet or a sun, but it's really difficult to say based on what we know right now where the origin of the object and what it's made of at all. But definitely, like Aster was saying, as we're able to get better and better spectra, as the volatile materials are starting to evaporate as they get closer to the sun, and we get spectra of that, we'll get more information about what type of materials we're seeing, and based on the gas that the comet will be ejecting. Yeah, like I said, it's difficult to say right now, but it's kind of crucial in the next couple of months to take these observations and to collect spectrum of the object as it gets closer and closer to the sun.
We're also very hopeful, of course, for JWST to take a look at this. That would be a massive, massive boom to take a look at this as it gets closer to the sun and as this coma becomes more active. There have been some discussions of this, and so I think we're going to be able to get something. We can also, even with these low resolution spectra, we can still see that it's got a kind of red surface, somewhat similar to Borisov. So I'm expecting it to have a composition somewhat similar to Borisov's, which is volatile rich, but a little bit weighted. I'm trying to remember which way it goes. There's a little bit more CO2 than there is H2O in Borisov. And so I would not be surprised if this object had something similar. I did not remember which way that went.
Yeah, that's correct.
And so I would not be surprised if 3I had a similar composition, but we'll have to wait and see as the outgassing gets more significant and as more spectral observations are taken when there's actually a significant coma.
Yeah, and to add on to that, you were right. It does have a more significant CO enrichment relative to the H2O. And that is, that's a bit different than our typical solar system comets, right? Because they're more rich in H2O and have relatively less CO, I think.
Now, you're doing observations, Tessa, tonight, as in this is very much ongoing. Tell us about what you're doing this evening.
Yeah, of course. So tonight and over the next 2 nights, I believe, if I have that schedule correct, but in my mind. But these are some follow-up observations that we're going to take after we took some images and spectra last week on July 2nd. On Tuesday, I believe that was Tuesday, we took some spectra, low-resolution spectra with the SOAR telescope, which is in partnership with Michigan State University Department of Physics and Astronomy. And we took some data last week, but now we're doing some follow-up this evening, actually, taking some spectra. We're hoping to take spectra, but it's not for sure since we're pretty close to the moon right now, but it is really exciting to see what we'll get. I think the best bet is just to take some images in some of the red bands and to see if we can get some better to calibrate some astrometric data rather than getting spectra tonight because of the uncertainty with the moon. But it's been pretty cool to see how this all shapes up with the solar spectra.
Well, thankfully, the moon moves and moves fairly quickly night to night. So,
Yes.
if not now, what other future observations are planned by your team?
We don't have any currently planned, but we do have the following night. So we have tonight and Wednesday night for observations scheduled so far. And then if the moon messes up our plans a bit tonight, I think we will probably do some follow-up in the next couple months or even weeks, since time is of the essence, to do some exposure over multiple nights. That will be better to constrain spectrum data.
There are also going to be joint spectral and photometric data taken in August or November, at least if the proposal goes through, the MDM Observatory in Kitt Peak. And then I happen to be aware of that there's some ALMA proposals being submitted. There's some JWST proposals and Hubble proposals for emergency observations being submitted. And so there's a lot of plans, but not both from our team, which I believe Tessa is on that MDM proposal.
Yes.
And from a lot of other teams looking into getting observations of this thing from now until November and December when it becomes undetectable.
Yeah.
Now is the time where it starts. Now that the first paper's out, now we get to see the flurry of snowflake papers coming down like snow.
Exactly.
And as people find out new stuff, and it's always fun to watch that because, you look on archive every day and, every few days paper shows up as people try to constrain it. Now, reddening, Aster, and that also is an indication of age, right? In other words, reddened objects, that's the interstellar medium doing that. Isn't that correct?
To some degree, yeah. So we expect that the ISM is going to help redden these objects as it passes through. And so that will indicate that it's relatively old. Of course, we don't have a lot of ISOs. We only have 3 of them, and we're not quite sure what their composition looks like. And so the thing that we're going to run into is it's very hard for us to determine, is this reddening definitely from the ISM, or is it red because this object is just red? And that's what these objects look like. And so we are doing our best to try to understand how these objects work and how they get older and how they change as they pass through the interstellar medium. But it's really a difficult to constrain question. And there are also even more sort of, I'll say, exotic suggestions. Like, I don't know if you've had Daryl Seligman on before.
Oh, many times, yes.
I don't know if you've ever talked to Jenny Bergner, but she and he had a paper 2 years ago now where they showed that as an object like ʻOumuamua moves through the interstellar medium, cosmic rays can produce H2 in the surface. And then the water itself just changes phase, which releases the H2 and causes the non-gravitational acceleration. And so you can have these sort of weird exotic effects of moving through the ISM that are very, very difficult to constrain and very difficult for us to understand, since they only occur in the ISM itself.
Now, the path again, back to that, Tessa. The closest this is going to get to a planet in the solar system is Mars, right? This will not pass anywhere near Earth, but it will pass by Mars, correct?
Yes, that's correct. The object will pass within, I believe it's 0.19 AU, which leaves a lot of great opportunities to do some observing with some missions that are already there, and also to perhaps directly image the object if we're able to pull resources and take advantage of that close approach.
I think that's one of the coolest aspects of this, in that we will be able to serendipitously observe an interstellar comet with a probe in orbit of Mars. I don't think that happens very often.
Definitely not, yeah.
Yeah, that's a new one. Now, the brightness of this object is very, very dim, obviously, but not necessarily dim for an asteroid, or an interstellar comet or object. Is this within the range of a very well-equipped amateur to also do observations?
I think so, yeah. I believe that it may be visible. I think that even a amateur astronomer was a part of some of the follow-up observation. I may be wrong. Aster, correct me if I'm wrong, but I believe that.
Going to be completely honest, I have no idea what the magnitude limit an amateur astronomer can see to is.
Yeah, I'm not sure either, but
It's currently magnitude 15,
yeah.
which is pretty dim. And I'm trying to recall the limiting magnitude of a telescope of a given size. I think you're going to need a pretty big telescope, certainly at least a foot, and very low light pollution. But you can do it with the meter-sized telescope, but those are not exactly amateur astronomer quality. I'm going to unfortunately say that I do not know the answer. My guess is it's in that bounds where maybe is a possibility. I'll also say that right now it's going to be very, very hard to make observations just because it's in the middle of the galactic plane. And so all the detections that we've had to do so far need very complicated algorithms to try to remove background stars that amateur astronomers will not necessarily have access to. It's just very, very difficult to separate this object out from its background. That's making observations difficult with even, with small or large pixeled professional quality instruments. And it's going to make things even harder for amateur astronomers who do not have the resources that we would.
Mm-hmm.
Yeah, that is a problem. Well, anybody that's looked at the Milky Way with a telescope, that's very, very, very dense. And picking it out, which is amazing it was discovered in the first place right now, at this time, because that's hard for even you astronomers to do. Now, what was the circumstances of the discovery? In other words, what went into finding and picking this out? What happened?
So Atlas, the instrument, is an all-sky survey looking for asteroids and comets. And it serendipitously, as many of these surveys do, found this object. It has very good background subtracting algorithms. And so it managed to pick it out and got astrometry over the course of a few days. And the orbit fit to that astrometry has an eccentricity of 6, which is just really ridiculously large and is absolutely inconsistent with a solar system object.
Yeah, isn't the threshold 1?
The threshold is 1. Yeah. And there's uncertainties on that number, right? But at plus or minus 2, still too big. Mm. And so the consequence that we ran into is that we found it like that. And then we have follow-ups to further constrain the astrometry to get better and better and better observations. And that ends up in the discovery itself. This is also sort of how we found ʻOumuamua and Borisov, although Borisov's a bit of a weird story. But ʻOumuamua was found in a very similar way, using the Pan-STARRS instrument. And we're expecting that this is going to be the primary way that we find ISOs in the future, is these large-scale surveys looking for asteroids, amongst other things, finding an asteroid, fitting an orbit to it, and finding that orbit is not at all equivalent to that of a solar system object. And then with that, we can start doing follow-ups and really nail down that it's definitely an interstellar object and take further looks at it.
The Vera Rubin Observatory has come alive and is now making observations.
We're all very excited about it.
Very timely indeed, and that's my next question, because they turned it on, looked at one spot of the sky, and discovered over 2,000 asteroids in a week.
Yeah, very timely occurrence.
I mean, it was just stunning.
I believe it was 10 hours of observation.
Yeah, it was just mind-boggling.
Yeah.
Of what use will Vera Rubin and that survey be in trying to characterize this new object?
Quite a bit, obviously. So actually, I'll say not for this new object. Rubin is not a targeting instrument. It is not going to be looking at 3I and trying to figure out its properties. It is primarily a survey instrument, and I don't know the exact fraction, but it's at least 90, as large as 100%. Of its initial 10-year time is devoted to the legacy survey of space and time, which is just a truly massive all-sky survey of huge amounts of data every night, finding transients like this object, finding transients in the extragalactic, in the galaxy, in outside the galaxy, and just really getting a very wide survey to pretty deep levels. That being said, it's a big telescope, but we're not going to be devoting it to looking at this object. The big thing that Rubin is going to be doing for us is finding a lot more objects like this. Depending on the estimates, somewhere between as many as 100 over the next 10 years, as many as 10 over the next 10 years. We don't really know, but that's what we're expecting out of Rubin as it comes online, is to find a lot more of these. And it's a very happy coincidence that we found 3I directly after Rubin came online. And the 2000 objects is just a proof of how powerful this new observatory is and how good it is at finding objects like this.
I found it very poetic that, the telescope originally was the LSST before it got named. And now the survey comes out as LSST.
Yeah.
That was on purpose.
Yeah. I'm excited about it because you're right. This is going to find many more objects. And for asteroid mapping, it's
Absolutely
just shocking. Very, very fine instrument. Doing observations in a way that we really never did anything quite like this. I mean, we have fall sky surveys and stuff, but nothing like this.
Yeah.
And it's very exciting that it's
nothing to these magnitudes.
Yeah, and the success it's already seeing is, it reminds me of the Webb Space Telescope. It was just stunning. All right, so it was originally thought when this was discovered that maybe an asteroid, but then a coma was spotted. What happened there? That one observation said, well, I didn't see anything. And then another observation said coma.
Comae are really hard to find, especially one this week. This coma is not very big. It's not coming out in a tail. It's just a sort of fuzzy cloud around the object. And in order to detect that, you have to have a telescope with small enough pixels that you can make out the difference of it's fuzzy right here and it's not fuzzy right next to it. And I think a lot of the initial observations are designed for large field of views and do not have the pixel resolution necessary to pull that out. So it's really just an observational constraint that it's really hard to detect a coma. And as we get better and better telescopes, not always say better and better, as we get telescopes with more and more pixels per square degree looking at this thing, we'll be able to see more and more of that coma. And hopefully we'll eventually get to a point where we can determine the difference between the central object and the coma, because you need to be able to do that to measure how big it actually is.
Yeah, and like we said earlier, like the field is very crowded in its current position. So being able to pick out the coma from all of that, it requires some reduction. And there is a good image inside of the discovery paper, the Daryl's first author paper that he just submitted and is on archive. There's a good image from the Canada, France, Hawaii telescope that you could see the activity a bit better than when you're just looking at the crowded field.
And you can compare that to the Atlas image, which is just, you can't see any activity in that. It's just a dot amongst the various other dots.
Right.
And so you really need this sort of high precision from a larger telescope that's designed for focusing on a single object, from something like CFH and something like that, to actually be able to detect these things.
Now, will that angle we're seeing it in, is sitting in the galactic plane, will that get better as it moves through the solar system? Will you have, the ability to take better observations if it moves out of that?
Yeah, it certainly will. And then especially after it moves away from its closest approach with the sun and it's like at a higher solar elongation, it will be easier. Like, I guess from Earth, it will be easier after that period, but also from the perspective of space telescopes as well. I don't know if Aster has anything to add to that, but
we'll get a lot better observations when it moves out of the galactic plane, and then we'll lose observations and then moves behind the sun, and then we'll just keep on gaining them and losing them as the moon moves around. And then after it passes the sun, unfortunately, it'll be behind the sun for its closest approach, so we can't make any observations then.
Right.
But after its perihelion passage, we should be able to get some decent observations as it leaves the solar system and then eventually just disappears. There is some discussion of turning some of the telescopes on Mars satellites to look at this object when it's at perihelion, because Mars will not be behind the sun. So that'll be very cool, but we'll have to talk to NASA, and somebody else will have to talk to NASA and see if we can get that working.
Now, this object is really, as we were talking, really moving through here. So at the speed that it's at, I don't see how we could catch up to it to get a closer observation. So is there any possibility, any plan, or is this just going to unfold too fast before you could plan something? And would it be useful in the future to build a reactive system in space? And I know there's such a thing as for asteroids is in the works, for interstellar objects? In other words, can we put something out there ready to go when something is detected and get samples of it or something along those lines?
Yeah, so this object is obviously too fast, and we would not have the mission parameters. We have to have, been working on a mission for years already to be able to catch this. There is some discussion of showing that there could exist such a mission that could have caught this object, but that mission does not exist right now. So there's no way it's going to be caught right now. But like you said, there have been people talking about doing things like Comet Interceptor and other missions like that, looking for opportunities to go out and grab comets when they get very close to the Earth. So there's been discussion of a mission like that for this object. And it's quite possible that if there's a fourth ISO detected while Comet Interceptor is online, we may be sending Comet Interceptor to 4I instead. That's up to the ESA and all that. But there's been a lot of discussion after ʻOumuamua that we should develop a mission like this. The funding just hasn't been there right now, and this mission has never been approved. I think we should do something like that, but that's sort of the problem we run into. Is there's a lot of things that astronomers think we should do, and that the funding just does not exist to do. And so it'd be very cool if we could do it, but we're in a tricky situation with, Congress and NASA have not approved the budget necessary to build that mission.
Now, my last question for today is this. With ʻOumuamua, obviously there were very odd attributes to it that led to, increasingly spiraling out their theories as to how to explain it. But yet Borisov, nothing special, as far as anything peculiar. It's just an interstellar comet, basically. Mm-hmm. Is there anything in the observations of 3I that is unusual and difficult to understand? Or does this appear to just basically conform to everything you would expect from such an object?
So far, it looks like a normal comet. We have not seen anything that I'm not aware of anything in any of the observations that is difficult to explain by saying it's a comet like Borisov. We don't have a ton of data, so we may find more mysteries as we go into it, but it is certainly much less weird than ʻOumuamua, and currently seems entirely consistent with being another version of something like Borisov. Tessa, would you agree with that?
Yeah, I would totally agree. And in the coming weeks, as we're getting more data, as 3I goes through the system and gets closer to the sun, maybe we could see something interesting happening with the tail, or as it develops and some of those materials start to evaporate. But so far, it's looking pretty standard. I agree with Aster.
All right. Thank you both for joining us today, and I wish you great luck, and I can't wait to find out more about our third discovered and confirmed interstellar object.
Thank you for having us.
Absolutely. Thank you for having us, and keep an eye out for both of our papers in the, I don't know what your time frame is, Tessa, but in the coming weeks, for me at least.
Yeah, for sure. Me too. In the coming weeks, yeah.
Yeah, so it'll be very exciting.
Yeah. Thank you.
Thank you very much.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.